Oh, cool. All right. Let's see what happens if I press play. Which are you seeing on Slack? Are you seeing this or that?
Share your screen. On Zoom, we're not seeing that.
Oh,
So
okay.
if you can share your screen, so it would be great.
Yeah.
Okay.
And is that the slide?
Yeah.
Wow, look at me using technology. That's great. So have you done any other talks for the club?
So you
Yeah.
are the first guest we've had.
Oh, wow. Okay.
Give honorary, guest. But
Dishonorary.
week by week, we go through
Okay.
a series of tutorials.
Mhm.
Like, well, yeah, each week is a new tutorial. We go through just this data cleaning features, feature engineering, and we're hoping to get this hackathon, this data set that you mentioned.
Cool.
We started with the basics with pandas and NumPy.
Yeah.
We looked into data processing and cleaning.
Yeah.
Just to
Cool.
give everyone a head start once they get their hands on data.
Cool. Well, this talk does come with a data set that you can play around with. We actually have an extended version of this data set, and the archive paper should be up maybe by Monday, which is pretty cool. Something we've been trying to publish and have been working on. So I guess I'll get started. Hey, everybody. If you don't know who I am, I'm Travis Desell. I'm an associate professor here in the software engineering department. I know a little bit of software engineering, enough to be dangerous, but I'm more of a data scientist, computer scientist. I'm the program director for the Masters in Data Science. How many of you are Masters in Data Science students? Okay. How many of you are in, say, computer science? Undergrad, grad? Undergrad? Okay, cool. And any software engineering? Yeah, okay, cool. So yeah, our IT brought me over here to help set up the Masters in Data Science, and thanks to all you data science students, I still have a job, which is great. Okay, so I almost gave like a canned talk about some of my other research, but I thought this would be interesting because it's really more applied data science and data engineering as applies to this club. So we're going to talk about the National General Aviation Flight Information Database. I did not come up with the acronym. That was I don't know, some 10 years ago, a colleague at my former university, Jim Higgins, who became actually the department chair for their Department of Aviation, started this grant. It's been funded by the FAA for maybe 10 years now, a long time. It's been ongoing. So it's pretty cool. So I'll talk about more of the data science, computer science, data engineering research we've done for this. So as an overview, I'll talk about what the NG-AFID is, talk a little bit about its design. I'm not going to go into too many details, but feel free to ask me questions. We'll talk about flight safety event detection. Maybe I'll even have Aiden come up here and do the presentation for a little bit if he really wants to, because some of this is his work. I'll talk about logbook data set mining. This was a lot of work done with one of my former students who's now just graduated in the spring and is now faculty at Dakota State University in South Dakota. So he decided to go back to the Dakotas after coming out here from North Dakota, which was kind of crazy. Then we'll talk about some more recent research doing predictive maintenance, and hopefully the flow of this will kind of make sense as I go through it. Okay, so what's the NG-AFID? So the NG-AFID was designed as a system to collect and analyze general aviation flight data. So what general aviation is, quote from Wikipedia, all civil aviation aircraft operations with the exception of commercial air transport. So basically, like if you're flying Delta or any of those, that's not general aviation, or aerial work. Weirdly enough, they do classify some aerial work as general aviation now too. But basically, it's like recreational flight and private transport. So what's the FAA doesn't like about general aviation is that despite their best efforts, the safety, and the accident rates and fatality rates in general aviation have not gotten much better over the last few decades. Whereas when it comes to commercial aviation, it's safer to fly a commercial airline than it is to drive your car to work, right? In terms of the amount of accidents that happen. So the FAA really wants to get the accident and fatality rates as low as possible in general aviation, and it seems to be a pretty hard nut to crack. So they're like, well, can we collect as much general aviation flight data as we can, do analytics to try and figure out, okay, how can we make general aviation safer? So that's what the NGAFID was developed to do. It started at the University of North Dakota, where I used to be faculty before moving here, in part because UND has one of the largest flight schools in the country. I think they have over 150, 160 aircraft at their airport. It's kind of funny. If you go to the Grand Forks Airport, it's got 2 small terminals, but on a lot of days, it's in the top 10 busiest airports in the country due to how many students are flying in and out of that airport. So UND generates a ton of flight data on a scale that not many other flight schools do. We have a couple other flight schools in there, Liberty University and Embry-Riddle, which are kind of 2 of the other biggest ones in the country. And what's that? Yep, exactly. So we have flight schools providing data from around the country. We have a few private pilots that are providing data around the country. You can make your own fleet and upload your own data as a private pilot. And we've been getting into other general aviation carriers that I think fall into that aerial work category. So some non-like commercial aviation, even like UPS and FedEx and some of these other and even the Army have non-military, non-commercial, but they have fleets of aircraft that are doing flying, and those are other things that can be contributed to the NGAFID. Okay, so over the last however many years, if we look up here, this is our aggregate dashboard that we developed because the FAA wants to know how much data is in the NGAFID and how much has been contributed over time. It's a little small, but if you can see there, and this was just from today, not too long ago, we have almost 2.3 million flight hours of data in the NGAFID that's been provided. That correlates to 1.15 million different flights, and actually, a flight, quote unquote, in the NGAFID could be multiple flights. What happens is when a student gets into an aircraft, it turns on, the flight recorder kicks on, and they may go out and they'll take off, they'll fly to another airport, land, take off from there, fly to another airport, land, take off, fly and land. Sometimes they even just take off, circle around, land, take off, circle around, land 20 times or so to practice taking off and landing. So one flight might actually be multiple flights if you think of a flight as the time between takeoff and landing. So we have a lot of data in there. This is all time series data collected from the flights, what's it called? The flight data recorder. So most of these, it's from a flight data recorder called the G1000. And depending on the type of aircraft, we could have anywhere between 20, 25 different parameters up to 80. I think even some go up to like 120. So you can think it, and usually they're per second data readings. So one flight could be, up to 100 different columns times an hour plus worth of data across each of them with readings every second. So it's actually quite a bit of data. Recently, UND has a few helicopter. So that data has been coming into the NGAFID as well. And we've even extended it on a recent grant to include data from unmanned aircraft systems, so drones, things like that, with the goal of, well, how can we make incorporating drones into the national airspace safer, right? The last thing we want to happen is have somebody piloting a drone and it gets flown into an aircraft, goes into the engine, and that's really bad. So the FAA has been very cautious when it comes to allowing unmanned aircraft flights to prevent accidents, because commercial aviation is very safe. They don't want to ruin that very, big part of our economy. Okay, so whole ton of data. We have data from almost 500 different unique aircraft in there across these different fleets. And we have 113 total fleets/private pilots. I think the majority of our data comes from maybe 4 or 5 different flight schools. And then we have a lot of other smaller things contributing data as well. Okay, so what do we do with that data? For some simple stuff, we provide exceedance or event detection methods. And so what an exceedance or an event is you can think of simple warnings where a pilot might have been doing something not so good. So one of these things is, okay, maybe they flew too high. If they fly over 14,000 feet, I think systems start to not work or they can't breathe. It's really bad because they don't have oxygen. So, things like that. So if we look over here, we have like airspeed, a pilot flew too fast, altitude, they flew too high. We have some things that we involving engine issues. So the CHT is the cylinder head temperature. There's depending on the aircraft, you could have 1, 2, 3, 4 more cylinders. If you have multiple cylinders, if the temperature of some of them start to diverge, one of those cylinders is probably stuck and it indicates an engine issue. So we could kind of detect that there. Some other kind of more interesting things, like if the engine shuts down before 3,000 feet, probably a bad thing because they could crash. One of the other fun things about this data is it does come from a lot of flight schools. So they do, sometimes we get like acrobatic flights in there because UND does have like an aerobatics team where, do loops and all this other stuff. So sometimes we get false negatives because students are actually practicing a problem to practice getting out of that problem. So if you think about stalling or turning off the aircraft engine in flight so they can turn it back on, so it's something they get used to. A bunch of things. High pitch is this way, up and down. Roll is this way. So if they turn the aircraft too hard, they could end up falling out of the sky. You don't want that to happen. Or if they're going straight down, it's not bad. These are things that flight instructors, the flight schools want to know about, so they can make flying safer. So some cool things we do here is we have an interface where they can look at trends. So for example, down here, it's the percentage of flights with a particular event over time. So if a flight school sees, oh, I'm seeing a lot more high pitch incidents, maybe I need to talk to my flight instructors, maybe I need to talk to my students and say, hey, we've noticed this problem. How do we get our students flying safer so we don't have these issues? Okay. We provide, and I can probably live demo this in a little bit and run a little bit of a risk, but we also provide an interface for looking at event severity. So each one of these dots is what did I select here? A proximity event, and I'll talk about that a little bit later. But basically 2 aircraft got within 1,000 feet of each other while they were flying, which is something you want to avoid, right? It looks like a lot, but I think 500 is the line where it actually becomes an issue. 1,000 feet is not too bad, but we're testing things, sure things are in there. And this is over 2 years or so. But anyways, we provide severity metrics. So given a particular event, so say you had a high pitch event, how high was the pitch? That's the severity. So one of the operators looking at this data can go in and say, in the case of proximity, lower is worse because that means they got closer together than they should have. Click on one of these and see, okay, what happened in these 2 flights? Do I need to yell at a particular pilot or something like that? Also, do note, some of these proximity events aren't necessarily bad because if you have aircraft flying in formation, they're going to be close to each other. So we provide different flight visualization capabilities. So here, probably should have changed the color, but these are showing the 2 flight paths of 2 aircraft. And then these orange dots were actually where the proximity event occurred. And if I move this over there, see that we can zoom in, you can see what's going on here. Display the flights on maps, cool type of stuff. So they can kind of go into look at the data, look at the flight paths, get a better idea of what's going on. Even look at, say, particular parameters. So maybe we want to look at the pitch of one of these flights. They can visually kind of look at the time series data for different times. So we provide a lot of like data visualization capabilities if people really want to take a deep dive into their data and see what's going on. Okay. That was the same slide. We even have 3D reanimation. Too bad Aaron's not here. He's been working on this a bit lately, but so this is like a 3D reanimation. And cesium. Yeah. And this is actually the 2 flights in with a proximity issue. And if I hit the play button down here, you'll see them flying around. So they can even reanimate multiple flights in their browser to kind of see what's going on, which can be also useful to like show to like a student pilot, like, hey, let's look at this flight. What went wrong? How can you fly better? Let's see if there's an issue or something like that. And unfortunately, let's say stop. And lastly, we provide an interface where users can define queries to look at this data. So in this case, if you can see up here, I want to define every flight where the aircraft visited GFK, which is the Grand Forks Airport. And I have a group over here. It also visited FFM, I don't know what that is, and VKX. I also don't know which one that is. But so it was Grand Forks and either of those two airports. And down at the bottom, the duration was over an hour. So it actually gives like a little bit of a graphical query builder if you've done like a MySQL query, where they can look up just various flight data so they can get through the data that way. Okay, so that's kind of a general overview of the NGA, right? We put a lot of data in there. We have ways to visualize, analyze, provide warnings and valuable information to help the people participating in the NGA make their flight safer. Okay, so just very high level system design and overview. On the NGA FID, we give them a web interface. Right now, users upload their data as a bulk zip file. So basically, what happens at most of the universities, this is starting to change now, but whenever one of these flights completes, they pull the flight data recorder off the aircraft, they download that CSV file into some directory that they have, and every week they'll compress all that data, they'll upload it to the NGA FID as a zip file. So we kind of do bulk imports of CSV files. One or two of our participating universities, Liberty and Embry-Riddle, have started to use this software called AirSync, which actually does this all wirelessly. So when the aircraft lands, it actually just wirelessly uploads the data somewhere. So we're hoping to get a direct link from AirSync into the NGA FID, where AirSync's going to directly put in data right after flights land. One thing we recently did, as this flight data gets imported, we actually calculate all these exceedances, and for the ones that were particularly bad, we'll send emails to our users saying, hey, we found these issues in your recently uploaded data. Maybe you want to log into the NGA FID and take a look at it and see if there's a big problem. Big thing, we don't want to lose data. So when the data gets uploaded, it gets put on a separate archival hard drive, and then also gets imported to our database. So we leave those uploaded zip files in their original format in an archive. So if anything happens, we can always repopulate the entire NGA FID. That would take maybe a month now, given how much data we have, but still, it's something you want to think about as a data scientist or data engineer. You don't want to lose data. Data is gold nowadays, right? There's stuff we can do with this data that nobody else can, so we don't want to lose it. Then we have a ongoing running daemon, which just looks for new uploads. When they're done uploading, it'll kick off the ingestion process where it reads the zip file, imports everything to the database, does the calculation of events, and just repeats that over and over and over to get new data. One interesting thing to think about here is originally the NGA FID stored all its data in one massive table. I think NGA FID 1.0, by the time it was decommissioned, this table had like billions or trillions of rows in it, because every second from a CSV file was stored as a row in this one monolithic massive table. Not how I would have done it, which is why I redesigned things a few years back. So what we do when we import all this time series data is, instead of doing something like that, we pull out every column and then we compress it as an array and store it as a blob. So when we pull in the column of data, we can calculate some nice things like what was the maximum value, what was the minimum value, what was the average value, which is actually pretty useful. So say if we want to calculate if a flight had a high altitude exceedance, if we can just look at the maximum value that we calculated when we were importing that column, and if the altitude didn't go above, if the maximum value didn't go above that, we don't even need to read that whole block of data from the database at all. The other nice thing about this is, since we basically treat the column as an array, we compress it before inserting it into the database as a blob. And we found that Down here in the left-hand corner, we reduced storage requirements by a factor of 5 just by compressing our blobs. And it actually speeds things up because memory, reading and writing is pretty, and transport is really slow. So we actually can get data to say the web page quicker because it's stored as a blob, and get it in and out of the database faster because the time it takes to compress and decompress is less than the time it takes to read the full thing from the disk or not. So it sped things up and it led to less database consumption. So things to think about if you're working with larger scale data. Sometimes you can get a whole lot out of compression because disk reads are slow. Doing operations in memory is fast. Okay, so let's see. We'll move into a little flight safety event detection. One fun thing we implemented for the NG aphid was ways to specify events generically. So we have, I think, like 37 of different events in the NG aphid right now for different airframes and things like that. Having to write a class to detect a particular event when we can actually define it pretty simple didn't make sense. It was kind of ugly code. So how could we make this a little bit generic? We came up with a JSON structure over here on the right, which basically groups things into like a Boolean. It's kind of like a Boolean query, because most of our event types are, well, if this parameter is above that and this parameter is below that or above that or whatever, for X amount of seconds, we had a problem. So we can basically set up a Boolean logic thing that looks at everything that happened at a given reading in a flight file and say, okay, did we violate this particular event? Then we have a couple of other things in there. So basically, how long do we need to have these things violated for, and how long before we treat it as a new event? Because one thing that can happen is, say, in the case of high altitude, what if they're flying right kind of at the limit and they're going back and forth, right? They're above the altitude, they're below, they're above it, they're below. Well, in that case, we could generate 100 events when it's really only one thing because they're kind of flying at the limit. So we have how long does the constraint need to be violated before we kick an event on? And then how long do they need to be out of that constraint violation before we turn it off? So this lets us kind of view events as a single kind of block of time versus having, every second. Actually, in the old NG aphid, whenever anything got violated for 1 second, it counted as a unique event. That wasn't particularly useful for our users. And also having it as a block of time, we can calculate that severity, right? So for the whole time the pilot was, flying around too high, what was the highest they flew? So we can get an idea how that was. So that was pretty fun. So we actually dynamically read this JSON from our database. We have a web page where we can specify our query for a violation and directly enter in new event types right from our web page, as opposed to having to hard code them every time. Made my life a lot easier doing that. Okay. Then we got into more kind of fancy event detection. So one of my PhD students, Josh, who's working at Meta for this semester, should be back in the spring, has been working on self-defined glide path and turn to final code, which is pretty much there. The idea here is for the turn to final. So the approach phase, like when you're about to land, is one of the most dangerous parts of flying because that's when you're most likely to crash, right? So one of the important things is the turn to final. So when you're making that last turn to start landing at the runway, if you go too far and you kind of wave back and forth, that's bad. You want to have a nice, smooth, indirect line in. So the self-defined glide path stuff over here, a little hard to see, but the red lines are where the pilot turned either too shallow or too late and had to waver back. So we have the line of the runway, and then how far, if you think laterally, how far did the pilot diverge while they were coming in for their landing? Self-defined, so that's the turn to final. Self-defined glide path is a little bit different. If you look over here on the bottom, we know about where the aircraft should be landing on the runway. And ideally, the pilot should be coming in at a straight line. If they're wobbling around up and down like this, that's really bad. You don't want to do that. So self-defined glide path calculates from the start of where that approach to the runway is. It'll calculate a line to where it needs to be, and then how far does the pilot diverge from that line going to the ground. We got some visualizations over here. So this one obviously is problematic because they came in low and then they're trying to fix things on their way down. Other things that are really important, if you're coming in from a high point and you're going too fast, that's bad because you're going to crash to the ground. If you're coming in low and slow, that's also bad because you might not have enough lift and the plane might drop out of the ground. So these are important things that take a little bit more than, oh, did this flight parameter go over this value for this long? You need a little bit more of an advanced analysis to determine if there's a flight safety problem or not. Okay, then this was one of the fun things I worked on, was proximity event calculation. So we have almost 1.3 million flights in the NG AFID right now. We want to know if any two flights in there got within 1,000 feet of each other. We can't just compare everyone pairwise because that would be n squared, right? That'd be a million times a million flight comparisons. Not ideal. On top of that, right, comparing two flights is a little bit slow, right? Because you have to determine where they are at the exact same time and how far they were away from each other at that time. A little tricky. So wrote some fun queries to do a little filtering here. So the first thing we did was time bound things, right? If the two aircraft weren't in air at the same time, obviously they could have a proximity event. So the first thing we check is, okay, what, I want to insert this new aircraft or new flight into the NGA database. What flights were in the air at the same time that it was in the air? Then the next thing we do is we bound by the latitude and longitude. If we look at the rectangle of possible coordinates of the one flight and the rectangle of the possible coordinates of the other flight, if those two rectangles don't overlap, they couldn't have gotten close to each other either. Okay, so on top of that, after we've filtered and filtered again, we actually found that by doing this, we'd only have about 30 flights matched to each other at any given time, like by time bounding. And then when we bound again by latitude and longitude, we reduced it to about 16. So whenever we insert a flight to the NG AFID for proximity, we only actually have to compare it to 16 other flights, which is not too bad. Okay, so then once we've grabbed two potential flights that could have a proximity event, we need to align them by time because they're not going to take off at the same time. So we have to shift things by time and then iterate through calculating with their lat and long and altitude what the distance is in three dimensions. And then if they drop below that, then we have an issue. So this was a little bit too complicated to do in our simple generic event calculator. But we got things down to proximity calculations taking about 3 seconds per flight. And when our flight schools might be batch uploading thousands of flights at a time, this is pretty useful. We don't want to have the ingestion time to the database be so slow, we can't keep up with the volume of data coming into it. So performance is key to keeping the NG AFID up and running, especially as it scales and we get more and more data. So I don't know if Aiden wants to take over. Sorry for picking on you, but you can come up to the next view. I'll take a little break.
Yeah, so as Travis said, well, first of all, thank you for introducing me. Yeah, so I got to work, I think it's been 2 years since I implemented this already, back in 2020. I got to implement detection of stalls, right? And so what stalls are, it's actually a very, very dangerous situation to get into. It's brought down a lot of planes, both general and commercial. Actually, the last major commercial aviation incident in the US was caused by a loss of control, which is similar to a stall. We'll get into that. But basically what happens is you're like this, this is actually an Embry-Riddle aircraft here. It's got nose up, its pitch is high, and it reaches this critical angle of attack value right at the apex of that curve. And then all of a sudden the lift just goes down crazy. Once you get above that angle of attack, you're losing lift like crazy and you're in a dangerous situation, right? And so that also brings us into the loss of control in flight, which can stem from a stall event, right? So a loss of control in flight, imagine that where the aircraft is stalling, they're basically falling out of the sky, right? And you add into a coordination factor, right? So the coordination factor, usually what happens is it's possible for one wing to stall before the other. So what'll happen is if one wing stalls prematurely, you'll end up like this and then start spinning out of control. Again, yeah, these are all, again, I mean, it goes without saying that these are things that you don't want to experience at all, like ever on a plane. But because of how safe and how proactive aviation is, they have student pilots practice go into these situations so that they can recover if they need to, right? And so what we found was that, or there was actually a fellow who did his, I think it was his master's thesis on this, where he found out a way, and moving to the next slide here, this huge behemoth of an equation here is a way to calculate per every time step that you see there's probability of A given B. Per every time step, what's the probability that you're going to lose control, right? What's the probability that you're going to stall? What's the probability that you're going to lose control, right? And so he came up with this nice equation, right? And we basically implemented it in the NGAFID so that whenever someone uploads a flight, it goes through all the time series data and just creates a new column called the stall index or loss control index. There's two of them, and stores it. And then it's just like any other time series object in the database, right? So actually, like Travis showed a couple of slides ago, if you were to go on the data visualization feature, you'd be able to see the stall index, right? And all the stall index, if you go back 2 slides, the stall index is really just a measure of how close you are to here, right? So it's almost a ratio and it's capped at 1.0. So basically, if I were halfway to a stall, right? If the critical angle of attack on a Cessna is around, I think it's around 17 degrees nose up. So if I were at, half of 17, what is that? I don't know, about, yeah, if I was around there, I would expect my stall index to be about 1/2, right? For 0.5, right? And so what we were able to do is make events from these. So like Travis demonstrated in our generic event detection, you can comb through the time series objects and see if one peaks, right? Or if one is above a certain amount for a certain amount of time. And for us, Shelby Ballou, who was again the creator of this equation, his assertion when he came up with this work was that it would be 1 for at least 3 time steps. So we were able to create that definition as a JSON object and get a bunch of events out of it, right? Now, here was probably one of my favorite parts of this entire project, was we got someone to go out and test it. So someone we work with, his name's Andrew, he's at Liberty University. He graciously volunteered to basically go up and fly and stall and lose control of his airplane a bunch of times, and risk his life basically for us. And while he did that, he brought a GoPro camera with him and mounted it, I think, I have 2 videos. So there's one that showed the angle of attack meter on the plane so that we could see if our calculations for the angle of attack was correct, right? And then one kind of just showing the general view of the cockpit, right? And so what we needed to do was figure out, is it accurate, right? Like we needed to figure out, and this kind of became our ground truth, right? And so they flew the flight, and afterwards, they went through and annotated it and marked where the angle of attack meter on the plane was indicating the critical angle of attack, again, like probably 17 for this aircraft. And then marked where they basically started the event and stopped the event. Another way they were able to do that is the aircraft has a built-in stall horn, which is where if you go above the certain angle of attack, in fact, if you get close to it, it'll start to, it creates a little vortex on the leading edge of the wing, and that goes into a little funnel that creates a noise, right? So you can kind of tell based on how loud that sound is, how close you are to stalling, and how high your or how high your angle of attack is, right? So
one of the issues here too, right? The flight sensors on these aircraft don't have angle of attack.
Yeah,
so you had to infer it.
right.
So the question is our formula for calculating the angle of attack correct?
Yeah, exactly. So, right. And so that's how, in fact, most aircraft, most commercial aircraft, I think, have angle of attack sensors, but pretty much all general aviation aircraft you see out there, the little props planes you see flying around campus, those won't have an angle of attack sensor. So we had to infer, and they got basically when I mentioned the angle of attack indicator that they were filming, This is an aftermarket one that they put on, and it doesn't even give you an exact value. It has like five lights, and then if it's too high, it'll be the top light, and if it's normal, it'll be the bottom light. So it was just kind of a way for us to measure ground truth, right? So yeah, but here's the thing, we found out that there was actually a delay in finding these events, right? So again, these aircraft, the sensors aren't as advanced as modern commercial airliners, right? It's not like something you're going to see on a 777. But so what we had to do, what we can do is we can use data that we know is good. In this case, that would be our altitude data. We know that that's always pretty much accurate because it's barometric. So it can tell you instantly what the data is or what the altitude is. And if you don't know, vertical speed is the first derivative of altitude with respect to time, right? So what we could do is just take a simple linear regression for 3 points in time, the time ahead, the time behind at the current time, and figure out what the vertical speed is there. And that's basically what we did. And it made our, made the readings and event detections much more accurate, much closer to the actual time of the event. Whereas with before, we were seeing them further away from the event, right? Also, yeah, so this is another part actually. So for the Cessna aircraft, which was the one we tested, when you get down to lower speeds, the airspeed itself is not accurate as well. There's this airspeed adjustment, you can see the point right here, that needs to be applied for airspeeds less than 70 knots. So we had to apply that as well. And basically what we did after this, once we came up with these changes, is we had three different types of implementations, right? So the first one was the vanilla implementation, where we had basically none of these adjustments. Second one, we just did a derived vertical speed, but no airspeed adjustment. And then the third one was both. As you might expect, both were the one version 3 here was the best performing. And we figured that out because the subject matter experts in this case are pilots and other, we also had another pilot who just kind of annotated the data from, he was at UND. He also was able to kind of give his 2 cents, and they all found based on a list of criteria that that the third one really is the most accurate, right? And I think we actually have, yeah, the results here. Yeah, so the ones that are highlighted are the ones that are the best. Yeah, version 3, you know, the percent valid is the highest, and how we measured that was basically how far from when the stall horn activates to when it ends, like the deviation from that, like which one has the least deviation, right? And so version 3 excelled at that. And yeah, here's a user interface example. If you want, I can go and show on the beta site, like the,
Oh.
Okay, 30 minutes. I can be quick. All right, do you mind if I go?
Yeah, I can bring it up for you. Is it on? It's not the main.
It's on beta.
Oh, okay. It's over here. What's the?
NG if it beta.
Data, all right. Can I type that in right? Cool.
And I can see that.
Go for it. If you can type over your shoulder.
Never done this. Right. Oh. Not used to your keyboard, Travis.
Sorry. Maybe slightly older maps.
Better than the. Oh wait, no, you know what? It's my email address. I have like 15 different instances of this running on like 10 different machines, so I use a. All right, yeah, so test flight. We basically, so all of these are just copies of it. They're just kind of left over. What we did was we basically went through and made like 4 different copies for each method of like how I was talking about like the different versions, right? But what's really cool, and this is what I think my favorite part of it is this red to green gradient, right? So green is where the stall index or your closest to AOA or angle of attack is low and not risky. Red is where it's risky, right? So this, I know for fact that what they did here was they did a very long stall. So from here at time index 1886, it was 1.0. Our angle of attack was 16.2. And that went all the way to time step 1835. Well, actually, so the flight was going from here to here. But you get the idea. Basically,
Half a minute.
yeah. And then if you go here too, you can also trigger the overlay. So these are the places where that algorithm basically detected that it was a stall, right? So it was prolonged for more than 2 or 3 seconds, and yeah, registered as a stall. So yeah, I mean that's basically it. And yeah, you can also see the data visualization. I think we should go all the way down here. Yeah, stall index. Yeah, so you can see like, you know, our stall index really got high at these indices or these time steps, right? And so the purple is where that was, right? So yeah, I mean, yeah, that's pretty much it for stall stuff. Travis, I'll hand it back to you.
Thanks. That was awesome. And it's kind of cool. You can see like it's highlighted over in here where the events happen. You can see, I mean, it's really easy to see. And also note when we slide this around, you can see the little circle move over on the flight path, so you can get an idea. So, some generally like this is some of the work we've done in terms of event detection for the NGA. Now we're gonna kind of change gears a little bit to logbook data set. Data set mining. Okay, so we have all this data in the NGA from the flight data recorders, which is really cool. It's all the sensor data. After a lot of begging and pleading to the University of North Dakota, I got one of their maintenance people to provide me with 5 years of all their maintenance records. So whenever a mechanic or whenever a pilot noticed a problem with an aircraft or a mechanic noticed a problem with an aircraft, there'd be a logbook entry saying, you know, on this date, this aircraft went into maintenance because of this problem. And then an entry that said, okay, this is what we did to fix it. And this is when we released the aircraft back out to be flown again. So what our hope is, okay, well, we have all this sensor data. We know the flights that would lead up to these particular maintenance events. Are we able to create models that would say, okay, well, if the flight data is looking like this, it's probably going to have this maintenance event, you know, some amount of flights in the future, so that, hey, maybe we bring this flight in earlier for maintenance to make flying safer, to reduce maintenance costs, right? Because if you can detect a problem earlier and fix it, you can potentially save yourself from more dramatic issues. So I was like, yes, finally got this data. This is a gold mine. We can do tons of stuff with this. Unfortunately, this logbook data is a mess. Here's some examples down here. It's whenever there was a logbook entry, it was free text. The mechanics just typed in whatever they wanted. So like lots of abbreviations, lots of misspellings, not the easiest data to work with. So now we had another problem. Okay, so how do we get generic, okay, these are the major types of maintenance issues that we have in this flight data. So we can then pull out, okay, well, here were the flights that led to these particular issues. And then here's flights that didn't have any issues with them that we can kind of use as a ground truth, like these were good flights. So my former student Farhad, who is now back in the Dakotas, set apart, okay, doing some natural language processing to cluster this logbook data into various different types of maintenance issues, so we could then pull data from the NGA to do a little predictive maintenance. Since these entries here, they're short, they use a lot of domain specific terminology, a lot of abbreviations that aren't standard abbreviations, right? In this data, AEC would stand for aircraft, not air conditioner, right? So models trained on Wikipedia text like BERT, a lot of the big models used by Google and other people that everybody's using in NLP don't work very well on this data because it's very different from what those models were trained on. It's one of the first problems we had. Okay, so Farhad and with Marco Sampieri, who just went on to George Mason University, I think, in Virginia, worked on some pre-processing pipeline. We actually ended up developing our own spell checker because the existing spell checkers out there would do things like take AC and make it air conditioner. Whereas for us, we needed to be something else. So can read through paper 1 and 2 for a bit of information on this. He made a web-based repository so you can go and download this data. And he found and collected a few other different logbook types of data for different domains like automotive domains, facilities maintenance, and other things like that. And the fun thing is they all have the same kind of domain specific abbreviation and other NLP issues to work with. Okay, so having developed a pipeline to kind of clean this data where we could, do spell checking to make it work the way we wanted it to, we looked into clustering the data. Everybody, for some reason, likes to use k-means. We invested k-means, LDA as another type of clustering, some hierarchical clustering in dbScan, which is my personal favorite clustering algorithm. If you don't know about it, read up on it. It's very nice because it will figure out the number of clusters and tell you outliers, as opposed to k-means where you're like, I have 10 clusters. What are they? Pretty good. We found dbScan to work the best. We did a bunch of pretty kind of cool metrics over here, like let's see, how many clusters we had for the ones where there's orange and blue. It would give us an idea of the orange is how many outliers there were. Non-dbScan didn't have outliers. Everything was going to be in cluster. So that's another nice thing about it. And then we measured on the left the intra cluster similarity. So inside a cluster, how similar, given our different distance metrics, were those logbook entries, and inter cluster similarity. So ideally, you want your intra cluster similarity to be high, right? You want things in a cluster to be similar, and you want things in different clusters to be different, right? So we measured that, and purity is a kind of a combination of the two. And you can see here, I think all these up on top with the orange over there, all dbScan. And for dbScan, we saw the most intra cluster similarity and the least inter cluster similarity with different pre-processing pipelines. So that we investigated, which is pretty cool. Okay, another thing we found out, so having clustered this data, we actually, Farhad and a couple of our colleagues actually went through and manually annotated this all for ground truth as well. Started looking into doing classification. So clustering methods, right, are unsupervised. You don't know the ground truth. You're trying to figure out what your data looks like. If you have labeled samples, in our case, okay, we manually put them into one of 37 different types of maintenance issues. Can we develop neural networks such that if we show it a new logbook record, it'll tell us which type of maintenance issue it was? So that's what we looked into. So, but the issue here is if we look at the distribution of the different types of maintenance issues we have thousands of examples of some of them, and then in others we might have 10 or 20. So it's massively imbalanced data that we had to deal with. So one of the things we played around with that we found helped out a lot for this was to use a method I had played around with a bunch of years back for computer vision to handle massively imbalanced data. So the idea is to have a feedback loop where initially you sample from every one of your classes at this randomly, such that each class is the same size as your smallest class. So you're just going to randomly sample from every class, and if your smallest class is 10, you'll just grab 10 things at random from every other class. What you then do is you train the neural network for a few epochs, and then you run the neural network over your entire set of training data. After that, instead of selecting randomly, you select the instances that did the work that the neural network did the worst on, so the things that knew the worst. So then you train it for a little bit more and repeat. So what you're doing is always feeding the neural network the instances that it knew the least about. And you're not feeding it stuff it had already learned. It's kind of like, you know, I don't know how popular it is, but there used to be like adaptive learning software. So like if you wanted to learn vocabulary, you could have a deck of flashcards in a program. And instead of just having it shuffle and show you everyone randomly, you go through and then the ones you got wrong, it'd show you more and you learn faster that way. It's the same idea applying it to a neural network to handle this class imbalance. So we adjusted how many epochs we did across a bunch of different methods such that we give everything about the same amount of training time. So the one difference with the feedback loop method is that, you know, say every 5 epochs, when you rerun over the training data, that's going to take a bit of extra time. So we gave the feedback loop method a bit less time. We gave random down, we also evaluated against randomly downsampling everything. So just random downsampling without any feedback loop, random upsampling, which would get less epochs because your smaller data sets would become larger. So we tried to give it every, you know, each method about the same amount of forward and backward passes as each other. So it'd be the same runtime. So adjusting for that, training BERT, an LSTM model, and a convolutional model, and oops, this last one is the DNN. He called it a deep model, but it was only 2 layers, so it really wasn't that deep. But a 2-layer fully connected, just regular neural network. We found that the feedback loop pretty much beat everything out with statistical significance almost every single time. So it was a very good way to play around with this data to handle that class imbalance. We also found, interestingly, the convolutional model did way better than BERT, which struggled, which is because the data set is so kind of unique and not what BERT is usually been trained on. So it's pretty cool. And I maybe have just about the right amount of slides. So then, okay, we have all this data in the NGA FID. We have 37 different types of maintenance issues where we know this aircraft with this tail number went in for this issue at this time. So what did we do? We went into the NGA FID and we grabbed the time series data from flights leading up to the maintenance issues, and then other flight data from where we knew a flight wasn't within X amount of a maintenance, like it was either right after maintenance, but also not within another maintenance issue. So like maybe they fixed something, they flew it a couple of times and there was another problem. We didn't want that data, right? So we wanted good, clean data for no issue flights, and then data leading up to these these maintenance issues, with the hope that, okay, maybe we can train some models that will help us predict if an aircraft should go into maintenance sooner than it normally would when a pilot would warn, like, oh, hey, things are starting to go bad. So my one PhD student, Han, and even helped us a little bit on this too, used a method that was based on convolutional multi-headed self-attention. So basically like a convolutional neural network mixed with a transformer. So this has been popularly used in natural language processing, but as far as we knew till now, hadn't been applied to multivariate time series data, which is our flight data. We also compared it to 2 variations on just a kind of an LSTM model for classification, short-term memory. If you don't know what LSTM is, it's a type of, if you've taken my neural networks class, you probably know it in detail. And convolutional gated recurrent unit, GRU autoencoder. And again, if you take my neural networks, if you haven't taken my neural networks course, you'll know all about these by the time you're done. As comparison. So one of the things we found was that if we just train the convolutional transformer vanilla with the data we had, it would overfit almost immediately, and we wouldn't get any good results out of it. So we're like, okay, well, how can we do better with this? We investigated 3 methods again from computer vision to do data augmentation to prevent overfitting. So one of the things we did was cutout, and we called it temporal cutout. So basically, if you think about your time series, it's like a 2-dimensional vector, all right, or a 2-dimensional tensor. We would just select a random kind of rectangle in there and set everything to 0. Which is what cutout does in an image, right? You have an image and it'll cut out a bit of it and just set it to 0 like a black box. So we tried that. We tried mix-up, which over here takes a random set of channels from one of our time series data sets and it kind of replaces them with another set of channels from another time series. So we're mixing data between 2 samples to kind of make them look more similar. And then cut mix, which kind of takes two clumps of data from two time series and averages them or scales them together, combines them together too. So these are things that people will do when training big computer vision problems to augment their data or prevent the neural network from focusing on particular pixels in an image, which helps the network generalize. So our thoughts here, well, the network was focusing on particular time steps or particular little bits of data that don't actually reflect the maintenance issue. So if we do methods like these, we can help the network do better. And we got much better training performance out of it, and our models didn't overfit anymore, which is really good. Looking through that, we found that when we added in these augmentations, the convolutional transformer outperformed these other methods by quite a bit, actually, and we were able to get around like 75% accuracy with the generic problem of did this maintenance issue, or did this flight happen before maintenance issue, or did it happen after? We weren't looking at any particular maintenance issue yet, but this is kind of future work. We have a couple papers in the mix for that. So this predictive maintenance data set that we generated for this problem is available here. There's even a Google Colab if you want to rerun Hong's code to do the classification tests and regenerate the results we had in that last paper. We have a new data set coming out that's much bigger, where we have everything divided up by classes. So we have flights representing this one. It's just, did it happen before or after a maintenance event? Our new data set, which I can send you the link to, it should be out by Monday, here's the 37 different maintenance issue types and which flights happened before or after which particular maintenance type. So what's cool about that is you can do things this way where it's just a binary problem. Some of the maintenance issues actually are like, we have a baffle issues, but there's like 5 subclasses of that. So you can do like a super, like you can do kind of hierarchical learning too on it if you want, kind of like the difference between Cypher 10 and Cypher 100. So you could just, is it a baffle issue or any of these like super classes, or if you want to go down into lower level granularity of, okay, it's one of these particular issues. And also, again, this data, the instances we have are highly imbalanced. So it's a fun data set to play around with if you want to work with class imbalance. And it's also a little bit unique in that it's time series data, which people don't work with as much, right? A lot of people are doing NLP, a lot of people are doing computer vision. Working with this multivariate time series data is actually really challenging, but it's, in my opinion, under-investigated because it's really interesting with some of its own unique problems. So yeah, any questions? Sorry, I think I took up most of the time, but I think I have. What's that? And also just this, I think in the last couple of weeks, we ended up getting another 5 more years of maintenance records from University of North Dakota. So we'll be increasing the data set even more. Is HDB scan like the hierarchical version of it? That's a good question. Farhad looked into some other hierarchical clustering methods and they didn't do well. I think on it, I wasn't really familiar with it, so that's probably why. It could be worth looking into because there is a little bit of a hierarchy in these maintenance issue types. So it could, I mean, if it's something you want to play around with, the data is open. More recently started to look into like data augmentation techniques, but in some cases for some of the maintenance issues, the amount of data we have is so limited, it's kind of hard to generate synthetic data without it just being the same as what we already have, because there's not like a lot of options. I think there's some really cool work to be done in terms of like data augmentation, where instead of like working at the sentence and word level, you convert that data into the embeddings, which is, it turns it into numbers into like a tensor, and then applying augmentations there in the tensor space. So you're not like actively working on the words and the sentences themselves, but rather like next level up. But Yeah, it's tricky because, you know, some of these we maybe have 20, 30 examples. So it doesn't give you a lot to work with to do a lot of these fancier models that can generate, you know, like a GAN or something like that. It's just, yeah, it's a fun problem. No, we didn't use Glove. What did Farhad do? We did generate our own embeddings using, I don't remember the name of the model. It's in one of the papers. And I can send some of the slide deck to Tolu and Ruben and send it out to everybody. I think we probably use one of the simpler embedding methods. I don't, it was like a year and a half ago. So the data set we had was all for this was unplanned maintenance. So it happened because a pilot noticed an issue, or you know, a mechanic noticed an issue. The recent data, the new data we're getting gives us we're also getting when every planned maintenance happened, which should be useful. Yeah, I mean, it's how long before they took off and whatever they did and how long it took for them to come back. So yeah, the length of the time series for each flight is different, which is easy for recurrent neural networks. For convolutional, and these other ones not as much. What Han did for the predictive maintenance is I think he padded some to get up to it and clipped others to keep them around a fixed length. Yeah, that's one of the big issues with time series data. Like it's all different lengths, so you have to do something or use some kind of recurrent neural network where you, yeah. Oh, sure. Yeah. So this is one thing I've wanted to do with this data for a while is just generic like anomaly detection. So we have all these kind of hard-coded exceedances where, okay, if this parameter exceeds this value, there's a problem. But I have a feeling there's a lot of maybe instances in the data where it's not flagging any of these exceedances, but maybe the combination of them getting close, or there's some other weird data in there, would be really useful to know. So I've had a couple like graduate capstone students start to look into the problem of anomaly detection in time series, but it's tricky. But it's an awesome problem, and if anybody wants to work on it, let me know, because there's actually different scales of anomaly detection in time series data. So you can think of, is my whole, you know, one of these flight files, one of these whole sequences anomalous, right? That's one type of anomaly detection, like the whole sequence was weird. But other things is a subsequence within one of those anomalous, right? And I think in this case, that's probably more interesting, right? Because maybe a lot of the flight is kind of normal, but there's a spot in it which is different or anomalous, and those are things we really want to know about. So there's like different kinds of like tiers of flight anomalies, of time series anomaly detection. So you can think about it at the whole sequence level. You can think of it as a subsequence level, and I think you can even think about it as like a, you know, per parameter type thing. And there's some cool surveys actually out there on anomaly detection in time series. It's fun problem. Yeah. In the spring? Yeah. We're trying to figure that out. I think either it'll be the section I'm teaching, I think, is in person. And we might have a second section be online, or maybe they might both be in person. But we have two sections of it in the spring.
What really presented this from this program?
Hmm?
What really presented this program? Students.
Oh, do you know Java? Okay. Do you feel comfortable programming? Okay, that's the big one. Then, if you understand derivatives a bit, it's, some people teach neural networks and machine learning, and it's very math and theory heavy. The way I teach it is very programming based. So if you know how to multiply and divide, and you know how to do simple derivatives, should be fine as long as you can handle the programming.
Know how to optimize it better.
Yeah,
Because we start from the time from like hours to minutes, it's optimized.
yes. So one of the first projects I worked on as a PhD student was that we were collaborating with people in the astrophysics department, and they were developing models to fit 3D models to the Milky Way galaxy, because they were working with data from the Sloan Digital Sky Survey, which is basically where every star is in the sky. And they were like, okay, we need computer scientists to help us with it. We need a supercomputer to be able to run these models, because they just take so long. Their code had like 6 or 7 nested for loops where they were recomputing a bunch of stuff in the inner for loop. And just by like moving stuff out of for loops and optimizing their code, we got it about 100 times faster without like doing anything else, just like cleaning up their code a little bit. So neural networks are actually very compute heavy. So if you're smart about how you write your code, it'll help a lot. It's one thing to write code that can compile and run, but it's another thing to write code that runs fast. My analogy, I can let you guys go in a bit, is you want to be very smart about being lazy in life and as a programmer. So think really hard so you can do the least amount of effort. So when you write code, you want to think really hard about how you can make the computer do the least amount of effort to get the same job done. That's computer science. It's being smart but lazy. Yes. Cool. Yeah, thanks for having me.